Hello, I'm Serena and I'm presenting our AAAI 2023 paper, The Perils of Trial and Error Reward Design, Misdesign through Overfitting and Invalid Task Specifications. Imagine you want to design a new environment for using or benchmarking reinforcement learning. How do you approach this? We'll focus specifically on the reward function today. To design an environment, we might use trial and error. First, we design a candidate Markov decision process. We use intuition and past experience to craft a reasonable reward function. Then, we would reuse an implementation of some arbitrary but reasonable RL algorithm to test the environment. We would then use that chosen RL algorithm to learn a policy. Then we would see if that policy looks right. If not, we might change some combination of the reward function, state representation, algorithm, and/or hyperparameters, and try again. This trial and error process is common. When we started looking into this, we surveyed 24 expert RL practitioners and found that 92% reported using a trial and error to design their most recent reward function. However, trial and error reward design is in contention with typical RL advice. For example, in their authoritative text on RL, Sutton and Bartow declare, "The reward signal is your way of communicating to the agent what you want achieved, not how you want it achieved." But even in their own textbook, Sutton and Bartow disregard their own advice. When designing a DynaQ+ agent, they replace the reward function by adding an additional term which encourages exploration. Why does reward design practice matter? Why be concerned about trial and error? Trial and error is a dominant reward design strategy, but to our knowledge, nobody has studied it. We should seek to understand its consequences, both good and bad. One known concern is that of unsafe shaping. Potential-based shaping is known to be safe, meaning optimal policies are unchanged. But trial and error reward shaping is typically not potential-based. A second known concern is the propensity for misspecification of reward functions. Does trial and error reward design make this problem worse? We also introduce a new concern of overfitting. Can a reward function that is effective with one algorithm be ineffective with others? In other words, can reward functions be overfit to learning algorithms and hyperparameters? And if so, how does this affect the science of reinforcement learning and what we understand about this discipline? Spoiler alert, yes, we find evidence of overfitting in reward design. In this paper, we study the implications of trial and error reward design. We do so empirically with a combination of computational studies and controlled observation user studies. Our work draws on 4 areas of the research record. I won't discuss these in depth here. 2 papers I'd like to highlight, though, are Singh et al.'s Where Do Rewards Come From?, which looks at whether some reward functions can support faster learning, and Knox et al.'s Reward Misdesign for Autonomous Driving, which alerted us to the widespread use of trial and error reward design and some of its consequences. So consider this simple grid world task, Hungry Thirsty. It's something you might see in an RL 101 class. Food is located in one random corner, and water is in another. The goal is for the agent to eat as much as possible, but the agent can only eat if it's not thirsty. If the agent drinks, it becomes not thirsty. If it doesn't drink, then it becomes thirsty with 10% probability. The state representation consists of the agent's XY coordinates as well as its Boolean hunger status and thirst status. A candidate reward function for this environment is a sparse reward function, 1 if the agent has sated hunger and 0 otherwise. But there are other reward functions which maximize the overall objective of eating as much as possible. For example, here's an unsafely shaped reward function which encourages the agent to learn to drink as a subgoal before learning to eat. To introduce our experiments, we need to establish some preliminaries. One such preliminary is the idea of a true task performance metric, which need not be Markovian. This is a metric which is computed over trajectories to assess behaviors. For example, in the hungry-thirsty domain, the goal is to eat as much as possible. So the true task performance metric here matches the sparse reward function. In each time step, when the agent has sated hunger, it receives 1 point. Now, let D be a distribution of learning contexts consisting of algorithms, hyperparameters, and/or environments. And then consider a sample of D, D1. We define a reward function, R1, to be overfit with respect to this sample if there exists another reward function such that the expected performance of a policy learned with the first reward function, R1, and learning context sample, D1, exceeds the performance of a policy learned with the different reward function, but the expected performance of a policy learned with the first reward function is worse when considering the full distribution D. Since this definition of overfitting is intractable to test, we consider a second sample of the distribution, D2. Instead of analyzing performance over the whole distribution, we compare to the performance between these two samples to check for evidence of overfitting. We test reward functions which consist of 4 values, one for each Boolean combination of the agent's hunger and thirst status. We test over 5,000 reward functions of this form. Our first hypothesis is that reward functions that achieve the best performance in one learning context can be suboptimal in another. This hypothesis tests whether the best reward functions can be overfit, as they depend on the learning context, i.e., the algorithms and hyperparameters. One tool we use for analyzing reward function overfitting is parallel coordinate plots, where we visually compare the mean cumulative performance across different learning contexts. In a parallel coordinate plot, intersections indicate overfitting. For all experiments, we found that the best performing reward functions differ across learning contexts in support of hypothesis 1. The best reward function changes with the hyperparameters, as shown here with the learning rate, and it also changes with the choice of algorithm too. Our second hypothesis is that the cumulative performances achieved with different reward functions are uncorrelated across different learning contexts. This tests how common reward function overfitting is. If it is a common phenomenon, correlation should be low. To test this hypothesis, we rank all reward functions for each experiment setting. We then compare the ordering of these rankings using Kendall's tau. We find the rankings of reward function performances are either uncorrelated or slightly correlated in all hyperparameter experiments. In the results shown thus far, we used Q-learning as the underlying RL algorithm. In the paper, we also tested these hypotheses with deep RL algorithms and similarly found evidence of overfitting. We're now going to switch gears and talk about our controlled observation user study with 30 RL experts. Users were first tasked randomly, either with designing a reward function using sliders as shown here, allowing them to pick a value between -1 and 1 for each Boolean state combination, or with picking an algorithm and its associated hyperparameters. The algorithm choices were restricted to DDQN, PPO, or A2C. Though the order varied, every user ultimately designed a reward function, picked an algorithm, and selected a set of hyperparameters. They then trained an agent and evaluated its performance using a few different plots. One such plot consisted of the undiscounted return, which is computed with respect to their selected reward function. We also found that human experts overfit their reward functions. For example, user P20 first tried a reward function which achieved a mean cumulative performance of about 140,000 with DDQN, but they ultimately selected a different reward function which achieved a mean cumulative performance of just approximately 1,000 with DDQN. In this study, we found that 68% of our users overfit their reward functions. In addition to finding overfitting, we also found evidence that people, experts, are simply bad at writing reward functions, even in simple settings like this grid world task. Hungry Thirsty has some harder and some easier configurations. On the left, the food and water are located 15 steps apart, so this configuration is hard. On the right, the food and water are only located 5 steps apart, so this configuration is easy. Forget alignment in the real world. 53% of RL experts wrote reward functions which failed to encode the task in the hard configuration for this simple grid world environment. For example, user P3's reward function fails to encode the task in the hard case. In this setting, the benefit of drinking outweighs the benefit of eating. In the hard case, these reward functions consistently incentivize getting water too heavily. They also tend to disregard the cost associated with traveling from the food to the water, typically in the hungry and thirsty state. We found that most, 83% of experts use a myopic design strategy of weighing state goodness to design their reward functions. For example, user P25 stated, "It's best to be not hungry and not thirsty, so I'll set that to the max, 1. Being not thirsty is better than being not hungry, and worst is at hungry and thirsty, setting that to -1. This myopic strategy focuses on the relative goodness of individual states, and it does not align with the RL optimization objective of maximizing expected discounted return. This strategy often leads to misdesigned reward functions, as it did for user P25. From qualitatively analyzing experts' comments, we particularly believe that people are bad at reasoning about reward accumulation and especially temporal discounting. This is interesting because it provides insight on how we might support people in crafting better reward functions. One takeaway from all this is that reward functions can be overfit to learning algorithms and contexts. This has implications for reproducibility in RL, and this means we must even more carefully and critically evaluate research contributions. One takeaway for practitioners is that they should consider constructing two reward functions, particularly when shaping or conducting trial and error reward design. One of these reward functions should be used strictly for learning, trying to support the fastest and best learning possible. The other reward function should be used for evaluation to facilitate comparisons across algorithms and different learning contexts. And lastly, we should work to support human reward designers by finding mechanisms to align the process of reward design with the RL objective of maximizing expected discounted return. The main limitation of this work is that we only tested with one domain. While this domain has significant richness, it's clearly not representative of all RL settings, so expanding this work to look at other domains is one compelling direction for future work. Second, can alternative models of reward or reward inference help? Can we support humans in doing a better job of designing reward functions? And finally, how has overfitting affected the research record? Where should we as a community focus our efforts as we yet again reconsider issues of reproducibility and comparison in our efforts? Thanks for listening. All of our code and data is online, and feel free to get in touch if you have any questions. Thank you.